So welcome to the next part of the video on additional maths. This section is going to look at the derivatives of functions that we've looked at before: exponential, logarithmic functions, and trigonometric functions, sinx, cosx, tanx, and so on. So just to be clear, this here, well, let me just get that right. This is the syllabus reference for this section. You can read here, we're looking at the derivatives of functions, specifically sine, cos, tan, e to the x, log x, and combinations of these. And this other section here is about integration. Prior knowledge, you need to already know the P1 material on calculus. You need to know the chain rule, which was P1. You need to know how to integrate and differentiate powers of x, so you should already know that. And the product rule and quotient rule we've just covered in these videos on additional maths. So that's what you need to know. So what are we aiming at? Well, if I can give a little advert or try to encourage you to look at this material, let's say that when you've done this material, you'll be able to differentiate anything. Okay, so it basically, almost any function that you can think of, you will be able to differentiate after having gone through these basic facts that I'm about to show you. Now, it isn't really true for integration. So if we think about the integration section here, they give you certain functions, this function, this function, this function, this function, and they expect you to be able to integrate them, but they don't expect you to be able to integrate anything, because it's a much more difficult problem. For example, they don't even expect you to be able to integrate this simple function 1 over x. Now you can certainly differentiate that. It's just minus 1 divided by x squared. That's an easy one. But you can't integrate that with the knowledge we're presenting you here. That's the next step. That will be covered in P2. So if you are a student of P2, you should be able to integrate that from, I think, chapter 4, but not in additional maths. Okay, so what's going to happen in this video, I'm going to show you some justification, but not proof. Justification, that means like explanation, let's say, of the main formulas. And by the main formulas I mean the derivative of sin x, which we'll look at, cosx, and the derivative of e to the x, and the logarithm, the natural logarithm of x. So justification, I'll show you some reasons why the formulas are what they are. I hope that will help you to remember them and to see them in the right way. And then we'll see how just from knowing these 4 basic examples we can figure out almost anything else. A huge range of other functions. Now I have to say the proofs of these formulas are a bit complicated, but the results that we're proving, the answers, are really beautiful. I mean, they are maybe the first time when I really started to appreciate how beautiful mathematics is, in particular calculus, is when I saw these results. So I'm going to try to explain them to you as best as I can, but not with detailed proof. So here we go. Let's start with sin x. So I'm going to show you a web page. This is from Wikipedia. On this page, the page is called Differentiation of Trigonometric Functions. They explain to you in some detail how to differentiate these functions. And the key idea is the idea of a limit Now let me show you this idea with a picture first. So this is my own picture. Here I've just drawn a circle, a radius line, and I've dropped a perpendicular, the red dotted line, which I've called x. Now we know that s is equal to r theta. We know that from P1 or wherever you learned that, if theta is measured in radians. So I hope you remember that's only true in radians. Now x, of course, using basic trigonometry, is just r multiplied by the sine of theta. So we can see just by looking at the picture that s is bigger than x, because s is the length of the arc of the circle, which is longer than the red dotted line. So we can write that r theta is bigger than r sine theta. So we see that the number theta is always bigger than the angle theta is always bigger than the sine of the angle if we're working in radians. Yeah. Now that's true, but what's much more interesting is what happens as this radius goes down and down towards this horizontal radius here. So you imagine a picture like this. If I could just draw a smaller two lines. Oops, there we go. Two smaller lines like that. Whoops. Okay, like that, and you imagine that the angle is very small. If the angle theta is very small, maybe we call it delta or delta theta, some very small angle, then we can see that the perpendicular, the red line, is going to get closer and closer in length to the arc of the circle. That should be a curved arc there. So we can at least see that it's probably true that theta and sine theta become closer and closer to the same number as the angle delta tends to 0. Or we could write that in a different way as sine theta over theta tends to 1 as the angle delta, as let's say as theta, not delta, as theta tends to 0. Okay. Now we also know that as theta tends to 0, cos theta doesn't tend to 0 but just tends to 1, doesn't it? So we're going to use that fact. Now let me show you the working out of the formula. The formula is based on the principle of taking limits. If you remember, the definition of the derivative of a function is a limit. It's a limit as some number h tends to 0 of f of x plus h minus f of x all divided by h. That's how we define a limit, and that's how we work out the derivative of powers of x. And let's see how all this comes together on the web page here to make a calculation. If we write the limit formula here, the derivative of sine theta is the limit as some small angle delta tends to 0 of the sine of theta plus delta minus sine theta over delta. But the sine of theta plus delta can be calculated using the sine addition formula, sine A cos B plus cos A sine B. So we can expand this expression into sine theta cos delta plus sine delta cos theta. And now we do a little bit of clever factorization. We rewrite this by taking out this expression sine delta over delta. That's multiplied by cos theta, and then sine theta is multiplied by cos delta minus 1 over delta. Now you imagine the number delta becoming 0, or getting closer to 0. You see that cos delta minus 1 is going to approach 0, because that's approaching 1, so all of this is approaching 0, so this part is deleted. And what's left is sine delta over delta, but we just decided that that tends to 1 as delta tends to 0. So the final answer becomes cos theta on the right there. So I'll now I'll now write this here, that the final answer is d by dx of sin x is cos x. And that's our first key result today. The derivative of the sine of x is cos of x if x is in radians, only if it's in radians. Because if it's not in radians, then this formula here, up here, does not work. It's not true. So this only works in radians, but we get this very beautiful result. And this result makes sense if you sketch out briefly a picture of sin x. Suppose we draw sin x from 0 up to pi. We know it looks like this, and we know that cosine x looks like this, going down to 0 at pi over 2, or 90 degrees. And this point here, of course, is 1. And now we can see it makes sense because, for example, when x is pi over 2, sin x has a maximum point, which means its derivative is 0, which is correct because cosine x is also 0 at that point. And when sin x is 0, it's increasing, which makes sense because cosine x is a positive number at that point. So that's the first key result. The second key result, well, there's a number of ways to prove this, but maybe an easy way would be to write, if we wanted to find the derivative of cosine x, we could just rewrite cosine x as the derivative of sine of pi over 2 minus x, and the derivative of that is equal to minus cosine pi over 2 minus x. Do you see why that's true? Well, because we can use the chain rule. This is a linear function of x. So just take the constant multiple minus 1 outside. Now cos of 90, or pi over 2 minus x, is just sin x. So the answer is the derivative of cos x is minus sin x. And you could also prove that using a limit formula if you prefer, but it's obviously more difficult. Now let's think about our third main task, which is the derivative of tan x. And why don't you pause the video and figure out how you could find that derivative. Okay, so the way to find this derivative is to use the quotient rule. Oops, I seem to have the wrong colour here, sorry. So the derivative of tan x is the derivative of sin x over cos x. And we're going to use the formula u over v, derivative is v times u derivative, minus u times v derivative over v squared. So that's, let's make a bit more room for this. That's the quotient rule there. So this is equal to cos x, that's v, times u derivative, that's cos x, minus u, that's sin x, times v derivative, that's minus sin x, using this formula up here. Note the minus sign, yeah, very important. Note this minus sign. Derivative of cos x is minus sin x. Now all of this has to be divided by what? Divided by v squared, which is cos squared x. Well, that's equal to cos squared x plus sine squared x, minus minus there, divided by cos squared x. Well, this is just 1, so this is secant squared x, which is 1 over cos squared x. So that's the derivative of tangent x. That's our third main result today. Okay, let me save there. Now we can use these results to figure out the derivatives of sec x cosec x and cot x. So that's a little exercise you could try by pausing the video and figuring out for yourself. What are the derivatives of sec x, cosec x, cosec x and cot x? Okay, so I'll show you the answer now. This is the derivative of cos x to the power minus 1, which using the chain rule must be minus sin x, derivative of cos x, times cos x to the minus 2. Well, if you think about that, that's plus sin x over cos squared x, so that's sec x tan x. So that's our fourth main result. Then we've got the derivative of cosec x. Well, that's the derivative of 1 over sin x. Using the quotient rule this time, just for variety, we could do it the same way as before. But let's use the quotient rule. Well, that's v sin x times du by dx. U is 1, so that's 0. Minus u, that's 1, times the derivative of sin x, which is cos x, and that's all divided by sin x squared, sin squared x, and if you think about that, that is equal to minus cot x cosec x. So that's our fifth result. And our sixth result is the derivative of cot x. So the derivative of cot x can be again calculated using the quotient rule. Use the definition of cot x equals cos x over sin x, and get sin x times minus sin x minus cos x times cos x all over sin squared x, and this works out to minus cosec squared x, and that's our sixth result. So those are the derivatives of the 6 main trigonometric functions. All of those results work only with angles in radians. So try to learn at least the first 2. The others you can work out for yourself. Now let's consider the next big example. This is maybe the most important one of all, the derivative of e to the x. Now this is a difficult problem, and I'm going to show you one way to approach it. Well, I suppose I'm going to show you 2, but I'm going to skip a lot of details because it's quite a difficult task. The main thing is just to know the answer. Okay, let me show you a few different ways to look at it. Let's start with the definition of E. You may remember this from an earlier video. So I showed you the idea of compound interest. But I just want to point out the definition of the number E, as you can see from this calculation, comes from something like 1 plus 1 over n to the power n. Now we could make this a limit with 0 if we swapped 1 over n and n. This would be limit 1 over n to 0, 1 plus 1 over n to the power n. So this is actually the definition of the number E. But don't worry if you don't understand that in detail. But let's think about this definition. This resembles something you've looked at before. Do you know what I mean? This looks like a binomial expression, a plus b to the power n. Now the binomial theorem, if we expand this out, you're going to get this expression. It looks very complicated. Well, I suppose it is very complicated. But the interesting thing is, remember, we were talking about the limit as n tends to infinity. So here's a slightly interesting question. What does this formula become if n is very, very large? As n tends to infinity, what does this tend to? Maybe pause the video and try to work it out. As n becomes large, you'll get something like this. Now what does this simplify to? If n is very large, then expressions like minus 1 times minus 2 over 3 factorial n squared will become very small, because n squared is in the denominator. On the other hand, focusing on this term, look at the first part, n times n over n squared. Well, that's just 1, so that would be 1 divided by 3 factorial. So as n becomes very large, the only terms which do not cancel out are the terms where n does cancel out in each of these fractions. So it's the first part of each of these fractions. It's n over n times 2 factorial, or 1 over 2 factorial, n squared over n squared times 1 over 3 factorial, or 1 over 3 factorial, and so on. And so what you end up with is something like that, which is an amazing formula which says that E is equal to the sum of the reciprocals of the factorials of all the integer numbers from 0. So if you like, you can get a calculator and add up those first 5 terms, or the first 6 or 7 or 8 terms, and you'll get a number that approaches closer and closer to E, which is 2.718281828, 45904, and so on. Okay, so you can try that. It converges very slowly, but you can try it. In the meantime, what would happen if instead of n in the original slide, let's go a little further back down. So if in the original definition here we replaced n with nx, now we would still have the limit as n to infinity, but if we had an x in here as well, well, cutting out a lot of details, I'll just tell you that what actually happens is you get this very intriguing formula. Whoops, I think I've just jumped out of the presentation there, sorry. You get this very intriguing formula. Oh, that's right, it's in the other presentation, that's my mistake. It must be in this one. Yeah, so you get this amazing formula which says that e to the x, here it is equal to 1 plus x squared over 2. So what's happening here is we've got the same formula with an x mixed in, and this actually gives you a correct value for e to the x for any real number x, right? Actually for any number at all. But of course this ... is very important. This is not a normal polynomial, it's a polynomial of infinite degree. There is no maximum power of x. Now let's just write out this formula and see where it leads us. So again, I didn't really prove that this is true exactly, but I gave you some indication. It happens to be true that e to the x is identically equal to 1 plus x squared over 2 factorial plus x to the 3 over 3 factorial plus and so on, repeating the pattern. What would happen if we tried to differentiate this expression? We know how to do that because it's just powers of x. Well, we get 0 for the first term, 1 for the second term. We get 2 times x over 2 factorial for the third term. We get 3 times x squared over 3 factorial for the next term. We get 4 times x cubed over 4 factorial for the next term, and so on forever. So what happens if you tidy that up? Well, you get 1 plus x squared over 2 factorial plus x cubed over 3 factorial, because 4 divided by 4 factorial is 3 factorial, and so on. And amazingly enough, you've got the same infinite polynomial here as you had to begin with. It's the same formula, you see? So what we've deduced in a roundabout way is that in fact the derivative of e to the x is actually e to the x. And this astonishing result is also a unique result, by which I mean that this is the only function whose value, the function value, is equal to its gradient. So think for a minute about what that means. Remember what gradient means. It means that if I look at a graph like the one shown maybe here, yeah. If I look at a graph like the one shown here, for some reason this is not showing up. Anyway, never mind. Look at these red dots. You see that, sorry, I'm just wondering, why is that not coming out? Okay, there's some reason I think I know why. I figured it out. No. There. Okay. So now let me go back to the original one. Here. So it means that if you look at this graph shows different exponential functions, and focus in particular on the pink one. As it turns out, on any of these graphs we have the property that the gradient, the dotted blue line, or the gradient of that tangent, is proportional to the function value. So here, for example, I have the function value 3.1 or something like that. Here I have the function value maybe 10.5, and let's say this function value is 3 times this function value. Well, then it will follow that this gradient, the gradient of this dotted line, is 3 times bigger than the gradient of this dotted line. So the gradient is proportional to the function value, but moreover, for the special case e to the x, the gradient is actually equal to the function value. So if, for example, we look at the number 9 here, and I go across to this point on the pink curve, which is e to the x, the gradient at that point will actually be equal to 9. And as I said before, it's the only function which has that property. So it's a very, very special function, e to the x. It's the only function whose value is equal to its gradient. So that's our next result, and there's only one more result we need before we can start doing examples. The last result we need is the derivative of the logarithm, or the natural logarithm of x. So I could ask you to figure this out for yourself, but I think it's too difficult of a puzzle, so I'll just show you how to do it. The only thing we know about the logarithm of x, the natural logarithm, is it's the inverse function. So if y equals e to the x, we know that natural logarithm is inverse function. It must be true that x is equal to the natural logarithm of y. Now, how can we use this fact to figure out the derivative of log x? Well, here's what we do. We take this equation and we differentiate both sides with respect to x. So if we differentiate x with respect to x, we must get the same as if we differentiate log y with respect to x. Now let's think carefully about this. The left-hand side is clearly 1. But the right-hand side, the problem is this is a function of y, not a function of x. So we must use which rule? The chain rule. We first differentiate with respect to y, log y, and then we multiply by the differential of y with respect to x. Now here's the trick. Remember that y is equal to e to the x. So dy by dx, according to the result we just got, is equal to e to the x also, which is equal to y. So I can rewrite this equation as 1 is equal to d by dy log y times y. And then I can rearrange and write d by dy log y equals 1 over y. And now I've solved the problem, haven't I? Do you see why? Because we were trying to find the derivative of log x. Well, we found the derivative of log y, but y is just a letter. We can change y to anything. So d by dx log x is 1 over x. And this is our final result today. So having all these results, we now know how to differentiate a bunch of different functions. But what about, before we go on to exam questions, what about integration? So I'm going to use a blue colour for integration here. I'm going to go back to all the results we've already seen and ask about integration. Well, look at the first one. Sin x derivative is cosx. Well, that means integral cosx dx must be equal to sin x plus a constant, yeah? That's just the inverse process. Remember, integral of the derivative is equal to y. Hope you can read that. The integral of the derivative of y is equal to y plus an arbitrary constant. So I can just keep using this principle again and again. Here, the derivative of cos x was minus sin x, so the integral of sin x dx, remembering the minus sign, must be equal to minus cos x plus a constant. Now what about this? Here we had the derivative of tan x was sec squared x. Well, it follows that the integral of sec squared x dx must be equal to tan x plus an arbitrary constant. So this is just the basic principle repeated again and again. Now I won't do it here, but obviously you can do that yourself as an exercise. Here we figured out the derivative of e to the x was e to the x, so it follows that the integral of e to the x dx is e to the x plus a constant. Okay. And then finally we worked out this one. The obvious deduction is the integral of 1 over x dx is log x plus a constant, but actually there's a problem with this. It's almost true, but it's not exactly true, and if you study P2 you'll find out what I mean. But in any case, as I said at the beginning, this result is not included in the additional maths course, so I won't say any more about it. Okay, now the formulas that we've written down are almost all of them are on the formula sheet, and the ones that aren't can be easily worked out. The main ones are e to the x, log x, sin x, and cos x. Going back to the syllabus, you see here they want you to be able to integrate ax plus b to the n, which you did in P1, e to ax plus b, sine of ax plus b, and cos of ax plus b. So we'll see how that works using the chain rule in the examples we look at next. So from now on we're going to look at exam questions. Here's our first one. Curve has equation y equals x e to the 2x. Find the x coordinate of the turning point of the curve. So let's do it over here. Part 1, x coordinate of the turning point. Well, dy by dx can be calculated using the which rule? That's right, the product rule. So we've got product rule, u, which is x, times the derivative of e to the 2x. Well, e to the 2x is not e to the x, so the derivative of e to the 2x is not e to the 2x, because we need to use the chain rule. Look at this. Let me write a little side note here. U equals 2x, du by dx equals 2, so that if y equals e to the u, and dy by du is e to the u, because that's the rule we just derived, then it would follow that dy by dx is dy by du times du by dx, that's the chain rule, which is e to the u times 2, which is 2e to the 2x. So we see here that to differentiate e to the 2x we need to take the 2 outside, just in the same way as we do for other composite functions. Now I'm going to delete that, but obviously you need to practice using the chain rule in combination with all these other formulas that we've just derived. So the correct answer here for the product rule is dy by dx is x times 2e to the 2x, that's the derivative of e to the 2x, plus the derivative of x, which is 1, times e to the 2x. So let's just simplify that a bit. It's e to the 2x, 2x plus 1. Now we want to find a turning point, which means we're finding a stationary point, so dy by dx must be 0, so x is minus 1/2, and that's the answer. Now for part 2 we need to find the value of k, for which d2y by dx squared is k, and so on and so on. So part 2 we differentiate again. We want the derivative of dy by dx, which is the derivative of e to the 2x times 2x plus 1. Using the product rule again, we get e to the 2x times the derivative of this, which is 2, plus the derivative of this, which is 2e to the 2x, times 2x plus 1. And we've been asked to simplify this into a form ke to the 2x times 1 plus x. So I've got e to the 2x 2 plus 2 plus 4x. So that's 4e to the 2x. So therefore k is 4. Now we're going to find out if the turning point is a maximum or a minimum. So to do that we need to consider the sign of the second derivative. When x is minus 1/2, I've got 4e to the minus 1 times 1/2. Well, that's positive, so it's a minimum turning point. We can use all the same principles you've already learned about calculus. So let's just double check that. X was minus 1/2, giving me minus 1 here and 1/2 here, so that's clear. Okay, let's look at the next example. I'll need more space to work in here. Whoops, wrong position for that. Okay, that's better. So here's our next question. The diagram shows part of the curve 2 sin x plus 4 cos x. Line is drawn, so that's just describing the diagram. Find the area. We're going to find the area of the shaded region. So what's the first thing we need to do? We need to find the area A1. If I just shade that in. And then we need to find the integral of y dx up to this point, whatever this is, x1. Okay, so from 0 to x1, and then subtract the area A1, that will give the shaded area. So it shouldn't be too difficult. Let's first write the function 2 sin x plus 4 cos x. Find x1. Well, how do we find x1? x1 is the hold on a minute. A line is maximum point at b. So we know that b is the maximum. Well, that means at x1 dy by dx is 0. Well, the derivative is 2 times the derivative of sin x, that's cos x, plus 4 times the derivative of cos x, that's minus 4 sin x. Well, then it follows that tan x1 is 1/2. Did I get that right? Let me just read the question again. 2 sin x plus 4 cos x. Derivative is 2 cos x minus 4 sin x. So tan x1 is 1/2. So for what it's worth, I'll just make a little triangle showing me that for angle x1 we have this triangle, and I'm now going to find the value of a, find y at a. Y of x equals 0 equals 4, so a1 is equal to x1 times x1 times 4, so it's 4 inverse tan 1/2, And finally I want to find the integral from 0 to x1 of y. Two sin x plus 4 cos x from 0 to arctan 1/2. Now integration is the opposite of differentiation, so I'm going to get minus 2 cos x plus 4 sin x 0 to inverse tangent 1/2. Okay, so we can see from this triangle what cosine and sine of x are. So that's equal to minus 2 cosine of inverse tangent 1/2, that's 2 over root 5, plus 4 sine of inverse tangent 1/2, that's 1 over root 5. And then I've got minus the function evaluated at 0, which is minus 2 times 1 plus 4 times 0. So this all cancels out, so I'm going to get plus 2. So the whole area is 2, but the area of A1 was 4 inverse tangent 1/2. So the area we want is shaded area equals the whole area, 2 minus 4 inverse tangent 1/2, which you could work out on a calculator if necessary. That's the final answer. Okay, let's look at the third example. Third example, curve has equation x cubed log x, and what I think we'll do is we'll ignore part 3 of this question, which will wait for another video. Let's first find dy by dx. dy by dx using the product rule is 3x squared times log x plus x cubed times 1 over x, which is the derivative of log x. So that should be equal to x squared times 3 log x plus 1. So that's the answer to part 1. Calculate the value of log x at the stationary point of the curve. Well, if dy by dx equals 0, well it follows that hold on a minute. If dy by dx is 0 and x is bigger than 0, so that means x squared is not 0. 3 log x is equal to minus 1, so log x is equal to minus 1/3. So remember, logarithms can be negative, but you cannot put a negative number into them. So here, for example, we can put x equals e to the minus 1/3, which is a positive number. Okay, so the last part of the question is a little bit more difficult, okay, because you don't know how at the moment. You don't really have any particular method to finding this integral. So you have to use the result of the previous part of the question. Now let's see how we can do that. It's a bit tricky actually. Need more space for this. Okay. So we already have the following formula. dy by dx equals 3 x squared log x plus x squared. So if we integrate both sides of this equation, well, first let me try and explain the idea. The idea is that in doing this differentiation, you got the function x squared log x as part of the answer. So that means that is how you can find the integral of x squared log x. So let's write this carefully. The integral of dy by dx equals 3 times the integral of x squared log x dx plus the integral of x squared dx. I hope that makes sense to you. Now the left hand side of that equation is just y. And this is easy. This is x cubed over 3. Now we're going to rearrange this to give us the function we want. X cubed over 9 minus y over 3 plus some other constant. But we already know y. Y is x cubed log x. So that's x cubed over 9 minus x cubed log x over 3 plus some constant. So this is the correct answer to the problem, although you could rearrange it into maybe uh, 1 minus 3 log x plus a constant. So it's actually very important that you understand the logic of that that last part, because it comes up quite often and it's quite difficult. Okay, here's my last example. And here we have, similar to previous ones, but we're going to find the derivative here of a quotient. So we apply the quotient rule, v sin x times du by dx, which is 2e to the 2x, minus u, that's e to the 2x, times the derivative of v, which is cosx. And this is all divided by sine squared x. Now if this is 0, it follows that 2 sin x minus cosx equals 0. But have we justified that clearly? Well, we could simply write that e to the 2x is positive for any value of x, and 1 over sine squared x can never be equal to 0. So because neither this nor this can be 0, it follows that this must be 0. So try and write it carefully, but that's the basic idea. Okay, last part, find the x-coordinate of the stationary point. Well, we just write 2 sin x equals cos x, so tan x is 1/2. And you can calculate x in radians to 3 significant figures using a calculator. Okay, so I'll stop there. Hope that was useful, and see you next time.